All right, we are going to tackle this AP check on electrolysis. So an electrolytic cell is one that we are going to actually have to add energy in to the system in order to have a chemical change occur. Basically, we're going to drive a non-spontaneous process in a direction where it will occur. So we have to add an energy source to this. So on the left-hand side in this diagram, we see a galvanic cell, which is of course spontaneous, and it has a positive voltage. And then the electrolytic cell on the right, we see this power source, and the power source is allowing us to drive this. And so it's a negative voltage, it's actually requiring energy in order to drive this process. And so in the one on the left, if we want to think about how these substances are changing. So not only just the transfer of electrons, but what's happening to the stuff at the anode and the cathode. So in this first one, if we have zinc, okay, and it shows zinc here, but I'm going to draw zinc down here as well. So we have zinc in our anode itself, and so we're actually going to be losing mass. Okay, so we're going to lose mass at the anode in order to be able to send one of those electrons on. So basically, we're going to deposit some Zn ions, okay, 2+ ions, and then we would have 2 electrons that would be free to then move through the system. Okay. On the cathode side in this particular situation, then we are going to have some copper 2+ that's going to be going and depositing some additional copper onto that cathode, and so we're gaining mass at the cathode. When we take a look at the electrolytic cell and we're driving this in the other direction, it's going to be actually the opposite of that. So here we see that the copper is going to be sending those 2 electrons on, and it's going to become the copper 2+, so it's going to lose the mass, and then the zinc will end up gaining it. Okay, so as those electrons come here, we're going to have that zinc that's going to gain those 2 electrons, and it's going to actually deposit zinc on the cathode, so we're going to gain mass here. And there's ways that we can calculate that loss or that gain of mass, especially when it comes to the electrolytic cell. A lot of times we'll be asked to do that. So electrolysis is determining time and amount of substances produced during that process. That's a lot of times what we do. And so we're going to see a new unit here called an ampere or an amp. And it's a coulomb of charge per second, so coulomb per second. And then, of course, we see that Faraday's constant, the coulomb per mole of electron. So these are kind of nice little problems to work through because they're really just dimensional analysis. And so we're given a series of data. And let's go ahead and take that here. So on the first one, how much time, so we want to know time. Okay, this is our question. We want to know time. How much time is it going to take to produce an amount of copper using electrolysis with 125 amps? And we don't really need to know anything else specifically about that. Remember that the amp is going to be equal to 125 coulombs per second. So that actually makes it pretty nice. And basically in general, what we're looking at is we have copper 2+ plus 2 electrons goes to copper. Okay, so that's kind of the general process. And we don't necessarily need to know a ton about that, but we do need to know how many electrons are being transferred. Okay, so we're going to start off with our 4.5 grams of copper. So we don't need to know what's going on the other half cell, I guess I should say. Maybe that's a little more clear. Okay, for every 1 mole of copper, we know on the periodic table that there are 63.55 grams of copper. And for every 1 mole of copper, we have those 2 electrons. Okay, so 2 moles of electrons. That are being transferred. And then for every 1 mole of electron, we have 96,485 coulombs. And then finally, the power that they're using for this is going to be 125 coulombs per second, or the amperage, I guess I should say. So 125 coulombs per 1 second. All right, I went ahead and calculated everything ahead of time, so I get 109 seconds. We actually see that there's only 2 significant digits in the 4.5 grams, so with sig figs, I would call this 110 seconds. Okay, so one thing we could be asked for is time. In the next example, we're actually asked for grams. Okay, so how many grams of gold could be plated? And so this is a plating process. We have an amount of time, 10 minutes, and we have an amount of amperage. So we know that 100 amps is going to be equal to 100 coulombs per second. And we know that that's going to be a transfer of 3 electrons, because if we have gold, which is a 3+ ion, which is what we're given here, it has to be 3 electrons. Oops. Likes to auto change that. 3 electrons to go between that and solid gold. Okay, so let's go ahead and plug in our values. So we're going to start with 10 minutes. Now, because we have coulombs per second, we want to get that into seconds. So 10 minutes. For every 1 minute, of course, there are 60 seconds. Okay. For every 1 second, we know that there's 100 coulombs. For every 1 mole of electrons, we have 96,485 coulombs. And we have 3 moles of electrons for every 1 mole of gold. Finally, we need the molar mass for gold. So for every 1 mole of gold, we have 196.97 grams. Okay. Now we just go through and do the calculation. We're going to use 3 sig figs since our 10 minutes is in 3 sig figs. Our amperage is actually in 4, so we're going to take the least of those 2. And we get 40.8, or I did, 40.8 grams of gold would be deposited. I wouldn't mind having that amount of gold deposited. That'd be great. It has to come from the solution, though. It doesn't come from just nowhere. Okay. So our last problem here is going to ask for gas volume. So we've been working with solids and solutions. And so in this particular case, we're going to work with liters. So we want to know how many liters of H2. Okay. So one thing we want to remember with liters is that there are 22.4 approximately for an ideal gas, and this is an ideal gas, liters of gas is equal to 1 mole at STP. We're going to make that assumption. Okay. So in this case, if we are doing the process of electrolysis of water, I'm going to write out that process. So at the anode, the reaction for water is going to be 2H2O is going to be changed to O2 plus 4H plus 4 electrons. Okay. And I think there's a diagram somewhere in our notes or in a video where we actually see what's happening with each one of these. I think the book has a diagram. I'd have to go back to reference the page. Okay, so for the cathode reaction, we're going to have 4H2O plus 4 electrons is going to give us 2H2 plus 4OH minus. Okay. Our overall reaction then, and this is always the case for the electrolysis of water, or the net reaction, I guess. 2H2O changes into 2H2 plus O2. Now, why would we have to go through and see the half reactions? Well, that's what's telling us the number of electrons that are transferred. Otherwise, we wouldn't know. Okay, so this is telling us we have 4 electrons that are being transferred. Now, you know that now, so if you ever were to see this again, you could actually use that, or you could use this method. Okay, so let's start to plug in our numbers. So we are going to start with our 1.5 hours. Okay, so 1.5 hours. We know that there are 60 minutes in 1 hour, and there are 60 seconds in 1 minute. You can actually do the 3600 if you'd rather. I just always write it this way. It's just a habit of mine. For every 1 second, okay, so for our amperage, for every 1 second, there are 300 coulombs. For every 1 mole of electrons that are transferred, there are 96,485 coulombs. For every 4 moles of electrons, now this is the tricky bit, we actually have 2 moles of H2. So make sure that's not per 1 mole of H2, that's for 2 moles of H2. And then we don't need to go to molar mass because we want to know the volume. Okay, remember, we want to know the volume. So then for every 1 mole of H2, we have 22.4 liters of H2. All right. So calculate that all out. I get 188 with sig figs. We should have only 2 sig figs, so that gives us 190 liters of H2. There we go. We just have